Given question, engine working on ideal Otto cycle has compression ratio is equal to 5. Initial pressure is equal to 1 bar. Initial temperature is equal to 27 degrees Celsius. Maximum pressure in the cycle is equal to 30 bar. For unit mass flow, calculate pressure, volume and temperature at various salient points of the cycle and the ratio of heat supply to the heat rejected. Assume gamma is equal to 1.4 and R is equal to 8.314 kilojoule per kilomole Kelvin. Let us understand given data with the help of pressure volume diagram of the Otto cycle. If we observe, process 0 to 1 is for the suction process. Process 1 to 2 where the air compression is taking place, and this is isentropic compression process, that means entropy remains constant. Process 2 to 3 is the heat addition at constant volume. So if we observe, the volume V2 is equal to V3 and the heat addition is taking place. Then 3 to 4 is the isentropic expansion process where this entropy of the air remains constant, and 4 to 1 is the heat rejection process at the constant volume, and 1 to 0 is for the exhaust process. So this is the pressure volume diagram. Now if we observe the given data, compression ratio is equal to 5. So it is the ratio of V1 by V2. So we have to write here V1 by V2 is equal to 5 and notation is R. So I will show here the notation R. Then initial pressure and initial temperature is given. So this process starts at point 1. So this is the compression process 1 to 2. So suction and exhaust is where this medium is taking inside the piston cylinder arrangement and the medium is exhausted outside the piston cylinder arrangement. So initial pressure, that means P1, and it is 1 bar. So standard unit is Newton per meter square. So we will write here P1, and how to convert this bar into Newton per meter square, that is 1 into 10 raised to 5 Newton per meter square. Then initial temperature, so temperature is known as T1, and for calculation we will always use the temperature in Kelvin. So this T1 is equal to 27 degrees Celsius, so 27 plus 273, that is 300 Kelvin. Maximum pressure. Now if we observe this pressure volume diagram, if we observe the point 1, 2, 3, 4, then pressure is maximum at point 3. So P3 is equal to, so 30 bar, that means 30 into 10 raised to 5 Newton per meter square. Unit mass flow rate. So mass flow rate is unity, that is 1. So its notation is M, small m, and m is equal to 1. Gamma is equal to 1.4. So it is the ratio of specific heats. So it is Cp by Cv. So it is 1.4. R. So this is the gas constant R. It is 8.314 kilojoule per kilomole Kelvin. So for the calculation we will use here joule per kilomole Kelvin. So 8314 joule per kilomole Kelvin. So we have to multiply with 10 raised to 3, and it is Cp minus Cv. So how to calculate R? It is Cp minus Cv. So this is the given data, and we have to find out the ratio of the heat supplied to the heat rejected. That means we have to find out heat supplied, that means Qs divided by Qr. Here is the question mark. We have to also find out pressure, volume and temperature at all these points. So we have to calculate, if we observe P1 and P3 is given, so we have to calculate P2, P4, then we have to calculate V1, V2, V3, V4, and T1 is given, so we have to calculate T2, T3 and T4. So these parameters we have to calculate. Now if we observe the process 1 to 2, so when we consider the process 1 to 2, then we will calculate all the parameters related to point 1 and 2. So first we will take V1. So how to calculate V1, that is volume at point 1. So it is the formula nRT1 by P1, because the temperature and pressure at point 1 is known. So what is this small n? So small n is equal to small m divided by capital M. So here air is medium for the compression used as a air, which is mentioned in the question, where this small m is known as mass flow rate, which is unit, that is m is equal to 1. And what about the capital M? So capital M is the molecular weight. So it is for air is equal to 29. So small n is equal to 1 by 29, which we have to use. R we have to use 8314. T1 we have to use in Kelvin, and P1 we have to use in bar. So for with calculation V1, unit is meter cube, 0.86 meter cube. Now we will calculate the pressure P2. So how to calculate? P1 V1 raised to gamma is equal to P2 V2 raised to gamma. So compression ratio, that is V1 by V2, is known. So if I transfer V1 raised to V2 raised to gamma this side, so we will get V1 by V2 raised to gamma is equal to P2 by P1. So V1 by V2 is R. So 5 raised to 1.4, and P2 is equal to, we have to multiply with P1. So this answer is 9.5 multiplied by P1 is 1 into 10 raised to 5. So P2 is, we will get in Newton per meter square, because P1 we have to take in Newton per meter square for calculation. So P2 is 9.5 into 10 raised to 5 Newton per meter square. Then V1 by V2 is equal to R, therefore V2 is equal to V1 by R. So 0.172 meter cube. Now we will calculate the temperature. So we have the relation T2 by T1 is equal to P2 V2 by P1 V1. So we will put the value. So P2 and P1 we have to take into bar, and V2 and V1 we have to take into meter cube. So for when we calculate, then we have to multiply with T1. So T1 is in Kelvin. So 1.9 into 300, which is 570 Kelvin. So if we observe, we get V1, that is the volume at point 1, P2 that is the pressure at point 2, then V2 that is the volume at point 2, and T2 that is the temperature at point. Now we will move to the process 2 to 3, where the heat addition is taking place at the constant volume. So here V3 is equal to V2, which is equal to 0.172 meter cube. So we get here the V3. Then we have relation P3 by P2 is equal to T3 by T2. So we will put the value P3, it is given 30 bar, so 30 into 10 raised to 5, P2 9.5 into 10 raised to 5, and when we multiply with T2, which we have calculated, then we will get T3 1800 Kelvin. Now we will move to the process 3 to 4, where the expansion process is taking place with constant entropy. Now how to calculate here this pressure P4? So we have relation P3 V3 raised to gamma is equal to P4 V4 raised to gamma. So if we observe, V4 is equal to V1 and V3 is equal to V2. So V1 by V2 we know it is equal to R. So when we take V4 raised to gamma by V3 raised to gamma, then we will get V4 by V3 raised to gamma. Now we will replace V4 with V1 and V3 with V2. So V1 by V2 raised to gamma, which is equal to R raised to gamma. Now we will put the value. So it is 5 raised to 1.4. P3 is 30 into 10 raised to 5. So P4 is equal to 3.15 into 10 raised to 5 Newton per meter square. So we will get this P4. Now we will move to the process 4 to 1, where the heat rejection process is taking place at constant volume. So V4 is equal to V1, which is equal to 0.86 meter cube. Now T4 by T1 is equal to P4 by P1. So we will calculate T4 with when we multiply with T1. So P4 by P1 we will put the value. So T4 is 945 Kelvin. Now we will calculate ratio of heat supplied to the heat rejected. So what is the formula for heat supplied? So it is the process 2 to 3 where the heat addition is taking place at constant volume. So for the constant volume we will use the specific heat at constant volume, that is CV. So formula is mCV multiplied by the difference in temperature T3 minus T2. So T3, that is the temperature at point 3, is higher than 2. So we will take the difference T3 minus T2. In the same way, what is the heat rejected? So this process is 4 to 1, which is taking place at constant volume. So we will use specific heat at constant volume, that is CV. So it is mCV T4 minus T1. So this is the temperature difference at 4 and 1. So T4 is higher than T1. So we will take T4 minus T1. Now it is given that the small m is equal to unit, that is unit mass flow rate. So m is equal to 1. CV, which is not mentioned in the question. So how to calculate this? So we know gamma is equal to Cp by Cv. So I will write here Cp by Cv is equal to gamma, which is equal to 1.4. Now we will convert this Cp in terms of Cv. Therefore Cp is equal to 1.4 Cv. So this is the relation in between Cp and Cv. Now we also know R is equal to Cp minus Cv. R is equal to Cp minus Cv. But this Cv is having unit kilojoule per kilogram Kelvin. Now first we will put the value of Cp. So R is equal to 1.4 Cv minus Cv, which is equal to 1.4 minus 1 into Cv. Now I will write the unit. So R is equal to kilojoule per kilomole Kelvin, and Cv is equal to, so it is equal to 0.4. Cv is kilojoule per kilogram Kelvin. So how to balance these units? So if I multiply here with capital M, so this capital M is having unit kilogram per kilomole. Now we will balance this. So this capital M is the molecular weight, and for air its value is 29. So if I balance this, so I will write here Cv is equal to R by M. So I will write here R divided by capital M multiplied by 1.4 minus 1, that is 0.4, which is equal to Cv. Now we will think about this unit. So we have to balance this. So Cv is having kilojoule per kilogram Kelvin, and this unit we will transfer to the left hand side. So R is kilojoule per kilomole Kelvin divided by kg per kilomole. So we will reverse it. So I will write here kilomole by kg. Now if we observe, this kilomole is getting cancelled, and kilojoule per kilogram Kelvin. So right hand side and left hand side is getting balanced. Now we will put the values. So R is having 8.314 divided by M is having 29 multiplied by 0.4, which is equal to Cv, and Cv is equal to 0.717. So this is the value of Cv we will put in the calculation. And T3 minus T2, so here is the data. T3 we have calculated T2 also calculated. So heat supplied is 881.9 kilojoule and heat rejected, so it is 462.4 kilojoule. Now when we take the ratio Qs by Qr, it is equal to 1.9.